So the bottom line, after going through all of those slides about deriving these formulas, is that we have very many formulas that we can use to rewrite trig functions into other representations. And our goal today is to use any or all of these identities that are listed on your paper to do so. This is going to be a question on FRQ4, guaranteed. So we do need to have these skills to get the point on FRQ4 for equivalent representations of trig functions. Okay, can I show you what some of these questions might look like? I want you all day to keep referring back to this table. You have your reciprocal identities, your quotient identities, the new Pythagorean identities that we derived, the inverse trig identities, and then eventually we'll get to the sum and difference identities and double angle. I will explain those later. Example number 1, it says the function f is given by f of x equal to tangent of x over cosecant of x. Rewrite f of x as a fraction involving powers of cosine of x and no other trig functions. Don't panic. Here's what we're going to do. We're going to take the function f of x and we're going to rewrite it in terms of sines and cosines only. So tangent of x. What is the definition of tangent of x in regards to sines and cosines? Yeah, we can use the quotient identity to rewrite this as sine of x over cosine of x. Remember how earlier I made a big deal about putting theta behind your variable or behind the functions here? If you drop the x, this is wrong. You have to include a variable when we're doing these problems. Let's also rewrite the denominator. Cosecant of x, how can we rewrite that in terms of sine and cosine? 1 over sine of x. Very good. So this is the reciprocal identity. Aren't you glad we reviewed fractions last class? Because I have a fraction on top and a fraction on bottom. What do I do to divide those? Keep, change, flip. So I'm keeping sine of x over cosine of x. I'm changing the divide to a multiply, and I'm moving the sine of x over 1 to its reciprocal. I didn't say that right, but you get what I mean. Very good. So I have sine of x times sine of x on top. That means it's going to be sine squared of x. Remember, you put the square behind the sin, not behind the x. Don't drop the x.
So if we do, okay, never mind. Yeah, you
No.
explained that before.
If you drop the variable.
No, if you put the square sign on the x, you're only squaring the x.
Technically, yes, unless you put a bunch of parentheses there to make sure you know you're squaring the sign. Okay, whoa, we're super close to being done because the question wants me to rewrite this to where there's only cosines showing. Maybe some powers of cosines, but no sines. So what I need to do is I need to look through my formulas to see if there's a way I can rewrite sine squared of theta to where I'm only using cosines. And it's going to come down to this formula right here. Can I solve this equation for sine squared of theta? How do I get just this by itself? Minus cosine squared of theta to the other side. So what I can do is I can say, well, sine squared of theta, sine squared of x, sorry, would be 1 minus cosine squared of x. And I didn't change anything about the denominator. At this point, do we have any trig value other than cosine in my answer? Trig function. No, I only have cosines. I'm done.
So that's because sine squared of theta plus cosine squared of theta equals 1.
You can solve it for sine squared of theta by moving cosine squared of theta to the other side. And so it says sine squared of theta equal to 1 minus cosine squared of theta. We can substitute. It's a puzzle, okay? Trig identities questions is a puzzle and they're really fun. But while we're learning, let's go ahead and write down what rule we used where to make this make sense for us. The first thing we used was the quotient identity. I'm going to write QI for quotient identity. On the bottom, we use the reciprocal identity, RI. Is that okay if I use those shorthands? Okay. Then I did keep, change, flip, so I didn't use any identities there. And then I multiplied. I didn't use any identities there. But what I did to go from here to here is the Pythagorean identity. Is it okay to use PI for you guys? It's the private investigator. Pythagorean identity. So your job is to rewrite these things in different forms so they either simplify down to a single trig function or to the trig function that the question asks for, because this one asks for powers of cosine of theta only or cosine of x only. Give me some questions. What do we got? Okay, let me show some work on the last part. Would that be helpful? Okay, so I started with sine squared of theta plus cosine squared of theta equal to 1. But I wanted to have some sort of way to substitute out sine squared of theta. So what I did is I subtracted cosine squared of theta to the other side. Right? Just pick it up and move it. Cross the line, change the sign. Bless you. So now I can substitute using this Pythagorean identity. Sine squared of x becomes 1 minus cosine squared of x. They're equal to each other. I can substitute them in and out. Yes? Better?
Was that more important? Yeah.
Okay. Let's do this next one together. We're not ready to go on our own just yet. It says, example 2, we have 4 examples here. It says, use identities to simplify the following. Rewrite each expression as a fraction involving powers of only one trigonometric function. We have 3 trigonometric functions to start this problem off. There's a really good rule of thumb here that you will want to change everything to sines and cosines first, because it's going to be very easy for things to combine or cancel when everything looks like a sine or a cosine. So at first, I'm not going to change anything about sine. I'm not going to change anything about cosine, but I will change cotangent to its, not reciprocal, quotient identity, which would be cosine of theta over sine of theta. They are multiplied. If we're writing down what we did, remember that was the quotient identity. Okay, let's do some math here. If I'm doing cosine of theta times cosine of theta over sine of theta, that's top times top, bottom times bottom. We're going to have cosine squared of theta on top and sine of theta on the bottom. Ooh, aren't you glad we reviewed fractions? If I wanted to add 2 fractions together, I know sine of theta is not a fraction right now, but we can put over 1 and then it's a fraction. What do they have to be able to add them together? Let's make them have a common denominator. What should I make the common denominator? Sine of theta. Okay. If I want these to both have a denominator of sine theta, what would I have to multiply that first term by to give it a denominator of sine theta? Sine theta. So sine of theta times sine of theta, sine squared of theta. Common denominators, add the tops like normal, which means now I have sine squared of theta plus cosine squared of theta all over sine of theta. We still have multiple trig functions floating around here, so we got to get rid of something. Do you notice an identity in the numerator? Pythagorean identity. Look at that row. What is sine squared of theta plus cosine squared of theta? 1. So that whole numerator changes to 1. This becomes 1 over sine of theta. Since we have a fraction involving only one trig function, we could technically be done, but let's pretend that this question said we want this in terms of cosecants only. We can also then use the reciprocal identity to change this into cosecant of theta. So either answer will work. I'm going to end on cosecant of theta because I can't help myself. I think it looks nice when we're not having any things in the bottom. No trig functions in the bottom if possible. Oh, wrong letter.
It's not that hard.
I know you were delivering letters, yes? Okay, you're good.
If I think of it like x and y's, then my brain's not x. Because we did this same exact.
Here we go. Cotangent squared of x minus cotangent squared of x times cosine squared of x. We're going to just start with some things that you notice. Do you notice anything interesting about these two terms? They're subtracted by each other. What do they have that's the same? The cotangent squared, yes? When we were solving trig equations in 3.10, when 2 terms had the same thing, what did we do with them? Look at my hands. What am I doing? Take it out. What is that called? It starts with an F. We factored out the GCF. That's what we're going to do here too. So we're going to take out that GCF of cotangent squared of x. What I have left over is 1 minus cosine squared of x. Okay, so here's where my spidey senses are tingling. Cotangent squared of x, I can change that to what? Cosine squared of x over sine squared of x. That's your quotient identity. I also could change 1 minus cosine squared of x. What did we change that to in this problem? Sine squared of theta. If we solve the Pythagorean identity, 1 minus cosine squared of theta is just sine squared, this time of x. So that's the Pythagorean identity. What do you notice is on top and on bottom in this problem? So sine squared of x is going to cancel out. The only thing I have left is cosine squared of x. I only had one trig function. I'm done. Powers of one trig function, I guess I should say. So you're using these identities in creative ways. An easy thing to do when you're stuck is to always change things into terms of sines and cosines, because a lot of times like this, stuff will cancel, and it simplifies very easily. Let's try another. 1 over tangent squared of theta plus 1. I have tangent squared of theta in the denominator. What can I change that to? Look at the middle row or middle column of the Pythagorean identities. Yeah, tangent squared of theta plus 1 is exactly equal to secant. So we can change this to secant squared of theta. That's a Pythagorean identity. Let's pretend this one said I want the answer in terms of cosines. So 1 over secant squared of theta, that's the reciprocal of cosine, so I can change this straight into cosine squared of theta. The problem on your, not Q, this is R. The problem on FRQ4, and I will get better at writing them, is going to tell you what it wants it to be left as. Kind of like this one says it only wanted cosines to be showing. That's going to be in the prompt. Okay, I should have written better questions, let me just tell you. Okay, some more creative things we can do. Let's say cosine is already factored out here. Okay, we're going to leave it factored out for a second because typically we would factor things out to see if things simplify. Let's go ahead and change secant of theta into its reciprocal. What is the reciprocal of secant? 1 over cosine. That is the reciprocal identity. Are your spidey senses telling you to do something here? Just in general, like, I see this and I'm like, well, if I put this up here, cosine over cosine would do what? Cancel out. So, like, let's try it. So we're going to actually distribute that back in there. We're not going to factor it out. We're going to multiply. Cosine of theta times 1 over cosine of theta is cosine of theta over cosine of theta. And cosine of theta times cosine of theta is cosine squared of theta. I know, how many times can I say this in this one problem? Cosine over cosine. Ooh, okay, that's 1. Do you notice this again? 1 minus cosine squared of theta is that Pythagorean identity we started question number 1 off with. This is just sine squared of theta. Our Pythagorean identity. You want me to name my dog cosine of theta? Don't tempt me.
Like 5 dogs.
I need 6, all of them. If I ever adopt 6 dogs at the same time, you best believe I will name them the 6 trig functions. Yes? Yeah, go ahead. I do want to draw your attention to two of the rows of this table that I didn't really talk about before. We have more identities here called the sum and difference identities and the double angle identities. These are formulas we're going to need to know, but they look kind of funky without explaining them. Do you see this double, this plus or minus right here in the sign of alpha plus or minus beta? Yeah. That's because I've written two equations in one. We're being lazy here. I need you to take the formula, read it as if you're only looking at the top sign, and then read it as if you're only looking at the bottom symbol. Meaning, if I'm doing the sine of two angles that are added together, that formula is sine of alpha cosine of beta plus cosine of alpha sine of beta. If I'm doing the subtraction, so the bottom part, sine of alpha minus beta is sine of alpha cosine beta minus cosine alpha sine beta. There's two formulas in one.
Why is the other one minus plus?
So glad you asked. Why is the other one minus plus? Keep the tops with the tops and the bottoms with the bottoms, which means if you are doing the cosine of alpha plus beta, cosine of alpha cosine of beta minus sine of alpha sine of beta. Cosine of alpha minus beta is cosine alpha cosine beta plus sine of alpha sine of beta. Top goes with top, bottom goes with bottom, the way we've condensed these down. More things we need to memorize. It is too late to quit. You can do hard things. All right, and then we have our double angle identities. These, again, are just formulas we're going to maybe use. The sine of 2 alpha is equal to 2 sine of alpha cosine alpha. And then the cosine of 2 alpha has 3 options. It looks crazy long. It's not. Take your pencil right now and then draw a line here and here. There are 3 options for you to use. I've just put them all in one row to save space. Cosine of 2 alpha is either cosine squared of alpha minus sine squared of alpha, or 1 minus 2 squared of alpha, or 2 cosine squared of alpha minus 1. We have 3 options. I was trying to save paper. Don't judge me. Okay, it's going to be tough because you're going to have to flip back and forth, but the questions involving these are on the back. Sorry. Question number 2 says, oh, we have 2 number 2s. Oh, well. Which of the following is equivalent to the expression 2 sine of pi over 14 cosine pi over 14? Do you recognize this looks like one of the patterns from that table? Yeah, which one does it look like? It looks like 2 sine alpha cosine alpha. Right? That's what it looks like? That is equal to the sine of 2 times that angle. So for us, the angle is pi over 14. If we do 2 times pi over 14, top times top is 2 pi, bottom times bottom is 14. This reduces to pi over 7. So this is actually asking, what is the sine of pi over 7? We have to recognize the pattern that they've given to us and work backwards. We are starting to recognize that this looks like the formula that's on the front of the paper that looks like this, which is equal to sine of 2 alpha. Just take the angle, pi over 14, multiply it by 2. It's the same as sine of pi over 7. That is double pi over 14. Example 3, the function k is given by k of x equal to 4 times the cosine of 2x. Which of the following is an equivalent form for k of x? Okay, here's what I noticed this time. I see cosine of 2x. I know it's multiplied by 4. We're not going to lose that one this time. But cosine of 2x has 3 versions on my notes, yes? Sure. Read off those versions for me. Cosine of 2x is equal to what? Cosine squared of x minus sine squared of x, or 1 minus or I have just made a list of all of those formulas. course, all of these are multiplied by 4, so this would either be 4 times cosine squared of x minus 4 sine squared of x, or 4 minus 8 sine squared of x, or 8 cosine of squared of x minus 4. And we're looking for one of those answer choices, which is C.
Is there an easier way to do this?
If it's a memorizing the formulas kind of game, we need to know these formulas. You can derive them from each other, but we are just trying to recognize these identities, these equal representations.
So that's a no. So I think we're gonna fail this.
No, we will be
I just need to
okay.
master everything else that we've learned so far, and I'll be fine.
Example 4 says, which of the following is equivalent to the expression cosine of 8 pi, cosine of 6 pi over 16, I think I said that wrong, you get it, minus sine of pi over 8, sine of pi over 16. Whoa, okay, that's a lot of things. I noticed that the cosines are together and the sines are together. Look back at the front of your paper. Which formula does that look like? Cosines together, sines together. It looks like cosine of alpha plus or minus beta. Let's figure out which one it is, though. If I see this minus sign in between them, is that going to be the sum or the difference of these angles? Look at the formula. Top goes with top, bottom goes with bottom. So since I see a minus, minus was on top, this is going to be the sum.
Minus is on the bottom. So
Correct, because for cosine,
wait, no, it's on the top.
in the formula version of it, when it's all spread out, the minus is on top. So when the condensed version, you take the top, which is a plus. I don't know how else to describe that without writing them all the way out. Which means, stick with me all, this is cosine of the alpha, that first one, plus the second one, alpha and beta. So glad we practiced fractions last class. How do we add pi over 8 plus pi over 16? Common denominators. We'll make that common denominator 16. That means this is times 2. So it's 2 pi over 16 plus pi over 16. 3 pi over 16. Is the answer choice C or D, by the way? They both have 3 pi over 16. C, because this is the cosine of the sum. It's all about recognizing the formulas, pulling them from the formula chart, and using them. These are tough, because it's a lot to learn all in one day.
Well, they're not even here.
Yikes. Example 5, the figure shows a circle centered at the origin with an angle of measure theta. Make sure you notice that this is theta. It's in standard position. The terminal ray of the angle intersects the circle at point P. The coordinate points of P are 5, 12. What are the values of sine of 2 theta? First thing we're going to do is we're going to write down that formula of the double angle for sine formula. So off of the front page, sine of 2 alpha, or in this case theta, is equal to 2 sine of alpha, theta, cosine of alpha, theta. This is just, I'm pulling it from the formula chart. We don't know the angle though, so it feels like we're stuck. However, we have the coordinate point P and the radius of this circle. What's the radius of this circle? 13. What's the x coordinate of this circle, or of this point P? And then we can go back and use our definitions of sine and cosine from the very beginning to answer this question, which means I'm going to do 2 times sine. Well, sine is y over r. And then cosine. Cosine is x over r. So glad we spent all this time on fractions. Y'all see my evil plan coming to fruition? Top times top, bottoms times bottoms. We can even multiply by the bottom of the 2. So this is 2 times 12 times 5. Let's start with things we might know. What's 12 times 5?
60.
Times 2? 120. And what's 13 times 13? 169. Voila. That's it.
What is that as an example?
What is the what?
What is that as an example?
We don't know the angle.
This is not the.
No, this is the value of sine of 2 theta. We still never found the angle because it doesn't matter. We have the point P and the radius. Last thing, stick with me, guys. Just like last class when we started with the reciprocal values and then we started solving equations with the reciprocal values, we can do the same thing with all of our identities. So now when we solve equations, we may have to join up with some identities to be able to do that. For example, it says solve 2 theta minus sine of theta equal to 0 for theta between 0 and 2 pi. So we don't have to write a general equation, but we are going to solve 2, what? Nope, sine 2 theta minus sine of theta equal to 0. Your spidey senses should start going off when you see a double angle, 2 theta. We can't really do anything with that because there's no like terms. This one doesn't have 2 theta in it. We can't like combine them in any way. We have to get rid of the double angle so that we can actually combine. So we're going to use that double angle identity, 2 sine of theta cosine of theta, as the identity of that double angle. What do you notice now is the same in both terms? We're going to go back to those skills. We're going to factor out sine of theta, which would leave me with 2 cosine of theta minus 1. Once they're set equal to 0 and factored, what do we do? Equal both to 0. And solve. Thinking about our unit circle, what are the values of theta that would give me 0 when I take the sine? 0 and pi, and then 2 pi, but 2 pi is out of range, or out of the domain. Okay, so there's 2 of my solutions. I have to solve this so that the trig function is isolated, so I'm going to add 1 to both sides, and then I'm going to divide by 2. So what are the values of cosine, or values of theta that would give me 1/2 when I take the cosine? Pi over 3 and? Quadrant 4. 5 pi over 3. There's my 4 solutions. So it's what we did in 3.10 and what we did in 3.11. It's just that this step right here, when we took the double angle identity and substituted this in. Otherwise, it's exactly the same. We're just adding tools to our toolkit to be able to solve these functions. We started off with the easy ones, then we added our reciprocal identities. Now we're adding our Pythagorean identities and some indifferent identities. Just to show you another example here, it says using a sum identity, oof, thank you for the help. Find the values of theta between 0 and 2 pi, no general solutions, where sine of theta plus pi over 3 is equal to 0. Glad they gave me this hint to use the sum identity. So what I'm going to do is write down the sum identity as if this is alpha and this is beta. And I'm going to use this color scheme to help us out here. The sine equation, I'll write down since it's on the other side of our paper, is sine of alpha plus beta equal to sine of alpha cosine beta, plus goes with plus here, cosine of alpha cosine of beta. That's what we're filling in. But for us, alpha is going to be the theta, and beta is going to be pi over 3. So if we solve it with our numbers, you're doing great, guys. Keep it up. it's telling me to use sine? Like, if,
No, like, how are you going to, never mind, I see. I figured out myself.
okay,
Because it's the angle measure doesn't change, it's just the.
correct. See how we've just substituted in our values? Let's do what we know. The things that we know are this and this. We know these. Wait, I wrote the wrong thing. I am so sorry. This should be a sign. Y'all gotta stop me when I'm doing crazy stuff. You're like, I would stop you at the beginning of class, Miss Quigley. I get it. So, question, what is the cosine of pi over 3? Cosine of pi over 3 is a half. That's from my unit circle. And what's the sine of pi over 3? Okay, great. Now, of course, all of these things we're solving here, so far I've just substituted my identity. We're actually solving this equation being equal to 0. So let's solve. I'm going to rewrite this just one more time. This is an extra step, but I think it will help everybody see what I'm doing in the next step. I'm going to rewrite this as sine of theta times 1 over 2 plus square root of 3 cosine of theta over 2. Do you see? I've just rewritten it so that it actually looks like a fraction for us. Do those fractions have a common denominator? Yeah. Hooray! Let's use the fraction rules we have where we can add together terms that have a common denominator. I hate that it's a fraction though. Can we multiply by something to get this fraction to go away? Multiply everything times 2. What's 0 times 2? Okay, so this is still 0 equal to sine of theta plus square root 3 cosine of theta. Now we have to get creative here, and we haven't done this particular step yet. I don't see any squares, so there's no way that I could use a Pythagorean identity. They all have squares in them. I already have things in terms of sine and cosine, so there's no changing something to get something to cancel out. So instead, what I'm going to do is I'm going to subtract the square root 3 cosine of theta to the other side. Now, why would I do that? Great question. Because now I can divide by cosine of theta. Cosine of theta over cosine of theta is going to cancel out. We end up with sine of theta over cosine theta. Why would I want to do that? It is now a single trig function. Which trig function is it? It's tangent. So now the question is, when does tangent equal to negative square root of 3? At 2 pi over 3 and at 5 pi over 3. This is a very complicated question. We have yet to see one where we had to use a reciprocal identity at the very end to get this to combine down to one trig function that we know. We hadn't had to do that yet. We're adding tools to our toolkit of things you could possibly try on these problems to solve.